Okay, in this video I'm going to continue on with my tutorial videos on thermodynamics and statistical mechanics. This is video number 6, and I'm going to speak about heat capacities, or specific heat capacities if you want. The previous video to this is adiabatic processes, where I proved that PV to the gamma is a constant. However, that's not actually relevant for this particular video. So the first thing I need to discuss is what is a heat capacity. So a heat capacity is the amount of heat required to go from the initial temperature to the final temperature. Okay, so it is the capacity of your body to store heat, if that makes any sense. So it's, if you think about it, it's very ambiguous. If I say, what is the heat capacity of your phone? Well, to go from 100 degrees to 120 degrees. It's kind of, we'll say, actually, how about this? What is the heat capacity of aluminium to go from 100 degrees Kelvin, or 100 Kelvin to 120 Kelvin? It's very ambiguous, because you don't know. Well, there could be, there could be a ton of aluminium. There could be 1 kilo of aluminium. There could be, it's very ambiguous. So usually what we do is we normalize the heat capacity to per unit volume. But anyway, the placeholder or variable we use for heat capacity is this, is capital C, is the heat capacity. And we talk about the specific heat capacity if we divide by the mass. And that's equal to small c, and that's the specific heat. So this is, of course, not ambiguous, because we actually have normalized it to a unit mass. So if you're talking just about the heat capacity, it's very ambiguous. But if you're talking about the specific heat capacity, it is the amount of heat required in order to raise the temperature of one unit mass to by a certain amount. That's really what it is. So that's what the heat capacity is. But we'll find out in a moment that there are two different types of heat capacity, depending on what the scenario is, or the way you actually put in the heat. So let's go and rewrite we'll talk about just the heat capacity and not the specific heat capacity. So I said it's the amount of heat required in order to raise the temperature of your body by a certain amount. Okay, there is the formula of it. That makes perfect sense. C is equal to Q over delta T. But we know that the first law says the following. Delta U is equal to Q plus W. W is positive when work is done on the system, and Q is positive when heat is put into the system. So if we rearrange that, we find that delta U minus W is equal to Q. So that means the specific heat capacity is equal to delta U minus W over delta T. So if you look at this formula, there are two different scenarios we have to look at. Well, or there are two different cases. We have to work out what happens when the work done is equal to 0. In other words, it is adiabatic. Oh, that's terrible. What am I saying? Adiabatic. That makes no sense whatsoever. Work done is equal to 0. And the second one is when the work done is greater than 0. You can't have work being less than 0, of course. So let's look at that. So we have two processes. Now, if the work done is equal to 0, it's a constant volume process, because we're talking really about compression work. So if there's no compression or expansion being done, well, then the volume is constant, and we talk about an isochoric process. So where delta V is 0, it's isochoric. Where delta P is equal to 0, it's isobaric. And when Q is equal to 0, it's adiabatic. Okay, it's good to get used to this terminology. So let's go look at the process when it is isochoric. So the volume change is 0. So isochoric, delta V is equal to 0. So if it's isochoric, we're talking about delta V is equal to 0, so it's constant volume. So I'm going to give the subscript V, saying it's constant volume. So let's say del A, del T, subscript D. This means the rate of change of variable A with respect to variable T, holding variable D constant. Alright, so if you remember your partial derivatives, we'll say del A del T dt, del plus del A del R dr. If you want, you could actually look at it this way. Each one of those partial derivatives has is something is being held constant. I'll do another one. Del A del M dm. So another way, if we really wanted to, we could write down here subscript T subscript R, subscript M subscript R, subscript M subscript T, because that's what a partial derivative is. But I suppose that's just being a bit anal. I'm just showing you that for completeness, really. So specific heat capacity, at constant volume C sub V is equal to delta U minus W over delta T, but we said it's constant volume, so the work is equal to 0, and we get that delta U over delta T. So where we're talking about infinitesimal jumps, it basically is del U del T. So we can say the specific or the heat capacity at constant volume is equal to del U del T. Simple as. And this is an isochoric process. Okay, and this is a very important formula. This is one of two formulas in this particular situation that you're going to need to know. So I'm going to rewrite that, saying that the heat capacity at constant volume is equal to del U del T at constant volume. And this is isochoric. Isochoric constant volume where the work done is 0. Now, if delta V is non-zero, then the system expands. Well, it usually expands. Doing work on the surroundings. Now, if the system is doing work on the surroundings, by our sign convention, W is negative. Delta U minus W becomes, as in delta U minus W is equal to C. Let's say that's what we had. So now it's delta U minus W over delta T is equal to C, or delta U plus W. So what we see in this case is that the specific heat is greater than the specific heat at constant volume. So when you actually do work, or when the work is negative, or when it's expanding, the specific heat is greater than when it is at constant volume. Okay, so so when the change in volume is not 0, when it's not isochoric, then you're going to be doing some sort of work. Usually it's going to expand, and if it expands, the specific heat is greater than when the specific heat at constant volume. We'll see in a moment what we're actually talking about here usually is the specific heat at constant pressure. Now, of course, if the system gets smaller, so it actually compresses or contracts, well then this does not hold. But where the system expands and the volume change is non-zero, then you have to do more work, or you have to put in more heat in order to change the temperature. So let's talk now about an isobaric process. Here, delta P is equal to 0. So we know that C is equal to delta U minus W over delta T. But if the pressure is equal to 0, it's going to be delta U minus P dV, constant pressure, that's your constant pressure process, over delta T is equal to delta U over T plus P delta V over delta T. So we can say that the heat capacity at constant pressure is equal to del U del T, constant pressure, plus P times del V del T at constant pressure. Okay? Now, I'm going to tell you that although this is del U del T at constant pressure, it is actually approximately CV. It's not exactly, because it's actually with respect to holding P constant. but it is approximately CV. But this term here is energy lost as work. So the whole point here is that when the pressure is constant but the volume can change, well then you have to put in more heat in order to change the temperature. And that should make sense because we're usually getting your system to expand. As I said, when the system expands, C is greater than CV. And in this case we're talking about CP, the heat capacity at constant pressure. Okay, so to rewrite that quickly, the heat capacity at constant pressure is equal to del U del T at constant pressure plus P times del V del T at constant pressure. And the specific heat, or the heat capacity at constant pressure, is greater than the heat capacity at constant volume because we have to do work on our surroundings. Simple as. Okay, so remember that the internal energy is equal to 1/2 NFkT, where the system obeys the equipartition theorem, and we know the specific heat capacity, or the heat capacity at constant volume, is equal to del U del T at constant volume. So if we do that derivative, we find that CV is equal to NFk over 2. Okay, and this allows us to calculate the number of degrees of freedom, because if we can get a number for this, if the heat capacity at constant volume, we know this constant, we know this as a number, and we're usually able to calculate the number of molecules, so we're able to get the number of degrees of freedom. So let's say for example, we calculate the specific, the heat capacity, and we calculate at 12.5 joules per Kelvin per mole. So per mole. So that per mole like that. So in this case, what we'll do is we know that R is equal to Na times K. So we can plug that in here if we want. Okay. So if we do that, we're able to make F becomes 2 times 12.5 divided by the value of our molar gas constant, which is 8.3, and we get a value of 3, and we find that we have 3 degrees of freedom, which is exactly what we expect for a solid. So I'm saying this is a good way of measuring the number of degrees of freedom is by the heat capacity at constant volume. So the law of Joule and Petit is the following: Joule and Petit. So solids at high temperature, CV goes to 3R. This is the law of Joule and Petit. Is one of the things actually which inspired quantum mechanics. So basically what we have is as follows. There's our vibrational energy, we have rotational energy and translational energy. Okay, and we find that in actual fact that all solids they will get up to 3R if you get sufficiently high temperature. So that might be I don't know, whatever. That might be aluminium, well this might be sapphire, and whatever. Okay, so all of them, all the solids at some stage will approach 3R for their heat capacity at constant volume. I'm running out of time on my video, so I'm going to hurry up here and prove the final relationship. So we know that Cp, the heat capacity at constant pressure, del U del T constant pressure, plus del V del T at constant pressure. Well, we know that the internal energy is equal to 1/2 NFkT, or del U del T at constant pressure is equal to 1/2 NF times K. We know by the ideal gas law that PV is equal to NKT. So that means del V del T at constant pressure is equal to NK over P. So if you plug both of these in here, we're going to get the following. So we're going to get now that C sub P is equal to NF times K over 2 plus NK times P over 2 is equal to C plus NK. Or the heat capacity constant pressure is equal to heat capacity constant volume plus N times K. And if you're talking about 1 mole, you have, if you're talking about a single mole, Cp is equal to C sub V plus R. And this is for an ideal gas and 1 mole. 1 mole of an ideal gas. And I know I picked it up there, but I'm actually running out of time. So thank you for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.